Hi, this is Jeff from the Ozark Mountains in Missouri, USA. Well, today we're going to try to do something to cool down our Commodore 1541 disk drives. While the video thumbnail exaggerates a bit, you can't really fry an egg on top of your 1541. They do get quite warm. Well, why is that, and what can we do about it? Those are both great questions, so let's jump right in and see what we can find out. Thanks to PCBWay for sponsoring this episode. They offer an excellent quick-turn PCB prototyping service, which now has a free upgrade to the 150-160 temperature range. And this is PCBWay's 9th anniversary, and they're having lots of promotions, coupons, sales, etc. So go on over to PCBWay and check them out. There are two formulas that will serve you really well when you're tinkering with electronics. The first is Ohm's law, which says V equals I R. That is voltage equals current times resistance. Why current is I don't remember anymore. Back when I learned it, we didn't use V, we used E for electromotive force. And the second one is Watt's law, which says P equals I V. Power equals current times voltage. We'll be concentrating on Watt's law here. So in a basic linear power supply, we have our AC plug. Plug that into the wall. And it comes into a bridge rectifier, something like this most of the time. And from here we go into a 3-terminal regulator like this. Let's not forget our ground on our rectifier. And of course there's a smoothing cap in here like this. And we have the output of our regulator. This is our regulator. Okay. So the most important thing to understand about a linear regulator is that the current in equals the current out. However much current you're drawing from the output is how much is going into the input. That is very, very important. So we'll say I in equals I out. Very important. To keep numbers nice and simple, let's say that our circuit over here that we're powering draws 1 amp at 5 volts DC. Okay, so we know, because we know current in equals current out, that we have 1 amp flowing into it. And with a linear regulator, we're going to need 2, 3, 4, 5 volts of headroom. The older regulators needed more headroom, so it wouldn't be uncommon for a 5 volt output that we would have 9 to 10 volts input. So let's say 10 volts just to keep everything nice and simple. So we have 10 volts at 1 amp coming in, 5 volts at 1 amp headed out. So where's this other 5 volts? Well, that's dropped across the regulator. If we were to measure from here to here, when this is drawing 1 amp, we're going to measure 5 volts across here. This is where the heat comes from because of power. When you hear the word power, when talking about electronics, think of heat. Power equals heat. So our power output, then, if we look at P equals IV, is going to be 1 amp times 5 volts equals 5 watts. But our power input is 1 amp times 10 volts equals 10 watts. So in this scenario, we are converting as much power to heat through the regulator as we are driving our circuit board. That is why these linear regulators get so hot. And it's a little more complicated than that, If you've ever had these supplies apart right after you've had them on, you've noticed that the bridge rectifier is a little warm, capacitors aren't perfect, that type of thing. But the lion's share of the problem here is the way the linear regulator works. A switching regulator, on the other hand, instead of this, you can think of it like having a really fast on-off switch, right? And so as the voltage starts to droop on the output, it closes the switch. When the voltage rises, it opens the switch. And it's doing this tens of thousands or hundreds of thousands of times a second. So we're only drawing current just as much as we need to. And although the switching regulator is not perfectly efficient, they're generally 90% plus, it's a lot more efficient than these guys. So the more voltage you have in excess at the input than what you're using on the output, the less efficient the linears are, and also the more current you're drawing out of the output, because you're going to have the more power loss here. So now we'll look at what we can do to take care of this in our 1541. You might be wondering then, well, can we use a modern switching power supply in our trusty old 1541 in place of the original transformer and regulators? Yes, you can do that. Some people have. They've gutted out the transformer and put a modern switching supply in its place. That will work fine. I was after something less destructive, and that would be reversible. Quite a while ago, I refurbished an old VIC-20, the type that had the 2-pin 9-volt AC input, and it used a big regulator inside to convert the 9 volts to 5 volts, and had a big heat sink, and got quite hot. I replaced that 5-volt regulator with one of these guys, which is a modern switching replacement for the old linear regulator. It's made by this company, EZSBC. And that worked out great. I got that idea from Chuck Hutchins. I'll put a link to Chuck's channel in the description. And ever since then, I've been wondering, well, can we do the same thing with the 1541? Since I was going to try this, I thought it would be fun to do some data collection and measure the temperature before and after replacing the old linear regulators with these fancy new switching ones. And I wanted to do this in a way that was reproducible by anyone with some basic things that's easily attainable. And a few years ago, I had messed around with some temperature logging using these Dallas DS18B20 ICs. It looks like a transistor, but it is actually a digital temperature sensor that you can talk to over I2C. And I dug out the Raspberry Pi I had been using for that, and I updated it. And I decided, well, since I was going to be using a Raspberry Pi for data logging, I will get out my Zoom floppy and build OpenCBM for the Raspberry Pi, so I can also control the 1541 through the Raspberry Pi. That way I can write one Python script that will control the drive and do all the data logging. We can kind of make this an automated experiment, and it's something that anyone can replicate. Our 1541 has two power supply rails. Our orange wire provides 16 volts AC. That gets regulated to 12 volts DC. The blue wires provide 10 volts AC. That gets regulated to 5 volts DC. So each rail goes through a full wave bridge rectifier, a smoothing cap, and to a regulator. This is the 12 volt regulator, and the 5 volt regulator is just here under the shield. So the first step we want to do is measure the current used by each of those rails and make sure that our switching regulators can handle that. The easiest place to do that is right where this plug is. And I'm going to unplug this to get set up here. I made up this little plug with just parts I had in the junk drawer. So we can unplug this guy, plug him in like that, and we have access to take this loose, connect an ammeter to both sides, and measure the current on each rail. First, we'll start out measuring the voltage. So for this, we don't need to run the drive. So I'll plug the AC back in, we'll turn the drive on. I've got my meter set on AC. Here we have about 16.4 volts AC. That's what gets regulated down to our 12 volts DC. And here we have about 10 volts AC, which becomes 5 volts DC. And notice I did this inside arrangement because it doesn't matter if you spin that around 180 degrees, you're still going to have the right voltage in the right place, and it's AC, so there's no polarity. Now, I'll get set up to measure current here, and we'll be right back. I've got the meter set up here to measure amps, and I have it in line with the 16 volt AC signal, which, remember, becomes the 12 volts DC. And I will turn the drive on. Let's watch the meter here. You notice we had a brief spike just up over an amp, and our idle current is about 220 milliamps. I'm going to pop a disk in, and I'm going to tell Python to copy a D64 to the disk. You can see the blue light blinking on our zoom floppy, saying we're talking to it. And now our current has jumped up to about 1.3 amps. It has ranged between 1.2 and 1.3 amps. And using OpenCBM, copying a full disk image to the 1541 takes about 1 minute and 45 seconds. It uses a fast copy method, which is really nice. And then when the copy's done, we drop back down to about 220 milliamps. And I've already measured the 10 volt AC side, our white wires here, and that is about 1.1 amps all the time. It doesn't matter if the drive is running or not. That provides the 5 volts to the circuit board. So now we have an idea of how much current this drive takes, and we'll have to see if our regulators can deal with that. Of course, we also want to measure the temperature of the drive before and after, and to that effect, I've got one of our Dallas temperature chips here on this breadboard, so we can measure the ambient temperature. And our drive has spouted this umbilical cord, which goes to another one of these sensors mounted on the inside of the lid, which is kind of right over this voltage regulator area. This area right here is where all the heat's generated. We have the voltage regulators, the rectifiers, and the transformer at the bottom. So this was a good place to instrument it. Now, I've already collected the data for the before. I did that as I was developing the Python script to run all this. So we'll go ahead and change out our regulators, and then we'll go into detail about how the data was collected. And we'll look at some pretty charts to see what difference it made. Okay, the replacement process isn't too bad. Of course, we've got no AC power coming in. We need to extract the board from this drive. This drive is the one I refurbed for the last video that I did. There we go. There's 2 screws on the side and that pops off. I have already marked all these connectors when doing the last video. Even if you think you're going to remember how these plug in, it's a good idea. That way you don't get things goofed up, potentially damage something like that. And then there are 5 or 6 screws around the periphery here that hold the board on. Maybe 7 or 8. Unfortunately, even though we're kind of slightly overtaxing the 12 volt regulator, we've got big heat sinks here. We aren't running it at a 100% duty cycle, probably maybe 30 to 50% at the most. I tested it with about a 30% duty cycle. just how that turned out. Okay, now I am going to replace these regulators one at a time to avoid making mistakes. Let's see. Took a while to find the right size socket for that. I didn't have the right size nut driver. It is 7/32. Guess they decided to not buy into the metric fad and stuck with the far superior imperial measurement system. There we go. And note that there is an insulator around these screws. Okay, there is our 12-volt regulator. And the pins on the regulator are slightly offset from center, so you can't get it rotated 180 degrees. That's just not possible. Took a little convincing to pop that guy loose. I'm going to put just a little heat sink grease on there to help out since we're overtaxing it, and we'll get that popped in there. Contrary to popular belief, more heat sink grease is not more better. The whole point of it is to fill in the slight surface imperfections so you have a larger surface area for heat transfer. It's going to be tricky to hold this little guy. Now, I have to do this in a couple stages. Okay, that guy goes there. I think I rotated him 180. Yeah, see what I told you about that not wanting to go in wrong? The pin's plugged in just fine, but the holes for the screws didn't line up. Oh, there was only one lock washer on here. Interesting. On this one, it's the same way. Here, there's a lock washer here, none there, lock washer here, none there. Okay, by tightening these down, I'm going to use the screwdriver, not the ratchet. These don't need to be that awfully tight. Even with the metal cans, if you over tighten them, you'll warp the can and you get less heat transfer. It's the same way with a 3-pin tabbed type like the 7805s. You don't want to tighten those too tight to the heatsink. Okay, I'm going to do the same thing for the 5-volt. We'll get these soldered up, put it back in the drive frame, and measure our voltage to make sure we have proper 12 volts and 5 volts. Okay, I've got the meter set up on a volt scale. Got our negative lead clipped to this capacitor right here. I'm going to put the positive lead on one of the 7400 series chips. Turn it on. We've got about 5.2 volts. Which would be okay, but we'll see if we can tweak that down a little bit. Okay, there we go. About 5.05. That's enough headroom. And for the 12 volts, we should be able to pick that up somewhere there, about 11.4. That's fine. And for the heck of it, I will set up to measure the current on both the 5 volt and 12 volt legs, and we'll see how that's changed. Okay, I'm set up here to measure the 16 volts AC, which is going to produce our 12 volts DC. I'll turn the drive on. And it jumped up to about 750 milliamps, and at idle it is about 145 milliamps. And now I will ask the Zoom floppy to copy a disk there. And that is now about an amp. So the reason we saw a current reduction on the input side is because we are using that current at the higher voltage, and the switching regulator, the current in is not equal to the current out. It's only using as much as it needs to keep the regulated voltage up to where it should be. Okay, now we're set up on the 10 volt AC input, which goes to our 5 volt regulator. Turn the drive on. And it is about 580 milliamps. And pop the disc in there and we'll make another copy. Yeah, it's bumping up slightly there. So we might say 590 milliamps sometimes when running. Now this poor disk, I've made many full D64 images, copy that to the disk, and I chose to do it that way. That way it's wearing along the whole surface of the disk, not just in one track. Yeah, so we'll say running current is 580, 590 milliamps. Okay, now we need to set up for the temperature test, which will involve getting all of this AC current measurement harness out of here, putting the metal shield back on, and putting the cover back on, which has the temperature sensor on it. And since we've had this drive running for a little while now, I'll need to wait a couple hours before running that test to make sure it is back down to room temperature. Okay, it's been a few hours. The drive has assumed room temperature. It's currently off. Here is the Python code. I'm remoted into the Raspberry Pi right now, so the video might be kind of choppy looking. There's some subroutines to create a CSV file. These funny looking lines right here, these are setting up periodic jobs at different time intervals. This one takes a reading about every 2 seconds, or 2 seconds between readings would be another way to do it. This is what starts the D64 copy. It starts at 240 seconds, 4 minutes past when the last one finished. And down here in main is where we set our file name, so we probably want to set this to something like running warm up switch. So our drive will be running and we're monitoring the temperature as it's warming up with the switching regulator. Drive enable true. If I want to run the same program without actually running the drive, we can set that to false, etc. I'll post all this on GitHub. There'll be a link in the description. Save that, and it'll run the file. It's starting all the periodic jobs. We're getting the first temperature readings. So I'll turn on the drive. And I've put the disk in it. You'll notice here where it says same one, same two. The way this data collection script works is that there hasn't been a temperature change. It won't record duplicate data points. So it'll just wait till it gets to the next change and it'll record the previous data point in the new one. It just saves, collecting the same temperature, every 4 seconds over and over and over again. If it's not changing, then, you don't need a separate data point for that. So this will take about an hour and a half with making the copies, it makes 15 copies and it waits 4 minutes in between each copy. So the total cycle time is about 5.75 minutes, 5 minutes, 45 seconds. The 0 you see in this column is telling us if it's run through the drive copy procedure. So this is XORed each time, so it starts out at 0. The first time it runs through the drive copy, or it's copying the D64, it'll get changed to 1, and it'll get changed back to 0. I wish I had done that differently now, but I'll keep it like this for consistency's sake. And when we look at the charts, we'll be able to see this as a square wave, and we can clearly tell from the temperature record when the drive starts running and when it stops running. So we'll just let this run, and I'll let it we'll just let this run, and we'll come back and look at the data when we're done. How did our new switching regulators perform? First, let's look where we're just idling the drive. It's not running the motor, and we can see by the orange arrow there that the delta T, the rise in temperature, was about 22 degrees Celsius. Now, the same idle warm-up test with the switching regulator, we can see the maximum temperature is lower, and the delta T is also about half of what it was with the linear regulator, less than 10 degrees Celsius. And indeed, if we chart both of those together, we can see that the switching regulator heated up about half over ambient that the linear did. That's a big improvement. Now here's our running test where the drive is running for about 1 minute and 45 seconds and then resting for 4 minutes, about a 30% duty cycle. We can see the temperature rises higher. This is the linear regulator here. And that square wave, each time the square wave switches, it is when the drive is turning off. And notice that our delta T in this case is 30 degrees Celsius. Now here we have the running test with the switching regulator. You can see the maximum temperature is lower. The delta T is only about 14.5 degrees C. And you notice on these running tests that we kind of have a stepwise function look to the graph. The points where it's steeper is when the motor's running, and then it kind of tapers off a little bit. The temperature increase does. That is when the motor's not running, but we still have some heat soak, and we get a little temperature increase. And graphing those two together, we can see, similar to the idle test, the running test shows us that we warmed up about half as much with the switching regulator as we did with the linear regulator. Again, a big improvement. Here's a chart that kind of summarizes everything. It shows the min and max for each test, the delta T for each test, as well as the delta T between, comparing the linear and switching test for both the idle warm-up and the running warm-up. The reduction in temperature is significant. This mod is well worth doing. It's easy, inexpensive, and completely reversible. Well, how about that? Just by replacing our original linear regulators with some fancy new switching regulators, we're able to significantly cool down our 1541. And thanks to the Raspberry Pi, our Dallas temperature sensing chips, and our Zoom floppy, we're able to collect some data and get a really good quantitative comparison between the original regulator and the switching regulator. Now, from a qualitative point of view, in other words, how does it feel? Yeah, we all know if you set your hand on a 1541 after it's been running for a while, it feels pretty darn warm. With the switching regulator, even after running for an hour and a half, you can put your hand on there and go, oh yeah, that's a little warm. But it doesn't feel bad at all. I even accidentally left this running all night in idle mode, the disk not spinning, and it was still just kind of lukewarm in the morning. So yeah, the switching regulators make a big difference. It's an easy upgrade, and it's non-destructive and fully reversible if you want to put the original heat generating regulators back in. Now, I'll put all the information in my program and everything, the links to that all down below. The one thing I want to warn you about with the program, the way I'm controlling this through the Zoom floppy, it doesn't recognize errors really well, and I'm not sure what to do about that. It was good enough for what I was doing, although I did manage to wear out one side of the disk by copying to it so many times. At any rate, if you have any questions or comments, I would love to hear from you. Yep, that comment section down there below, that's what that's for. And thanks to everyone who helps support the Hey Birt channel through Patreon and other means. It's greatly appreciated. And until next time, bye.